Well, joint distributions. Let x and y be two discrete random variables. Then we defined p of xy that is equal to the probability that the random variable x is equal to lowercase x and that y is equal to lowercase y. And this is called jointly distributed mass function. So in other words, we are given two discrete random variables. We are defining a new mass or like a probability distribution such that it returns the probability that x equal to x and that y is equal to y, like at the intersection or at the same time, that x equal to lowercase x and that y is equal to lowercase y. This function satisfies always is greater or equal than 0. And the sum over all the x values and the sum over all the y values should be equal to 1. And the probability that the two random variables x and y belongs to a given event A is equal to the sum of the joint distribution but over all the pairs that belongs to A. And conditional the probability that x is equal to lowercase x given that y is equal to lowercase y is equal to p of x and y divided by, oh, I'm sorry. First, I have to define the marginal. I'm sorry. I went one step forward, but no problem. Now the marginal probability mass function of x. This is from the joint distribution. You want to get the probability only for x, you can add the joint distribution but only along the y values. On the marginal probability mass function of y is pyy, but again you add the joint distribution but only over the x values. And now the conditional is the probability that capital X equal to x and capital Y is equal to y is the joint distribution divided by pyy. And the same happens when we have the probability of x I'm sorry. Probability x is equal to x given that y is equal to y. Is the joint distribution over the probability of y, the marginal probability of y. There you go. All right. Of course. Oh, I forgot something. Before we see the example. Probability of y that y is equal to y given that x equal to x is the joint distribution at xy divided by the marginal probability of x. And independence. Remember the definition of independence that we covered before for, we can say, common probabilities, not when we're talking about random variables. We say that x and y are independent if the joint probability mass function is equal to the marginal of x times the marginal of y. For any x, y, where x and y for any x and y that are values of x and y. So we have all of the definitions. So essentially here, I want to talk about, this is when you're working with two variables, we can say, here we have two random variables and we are giving some definition, but the point is that we start with the definition that the two random variables, they take on some value. So based on that, we have defined all the other things. Even notice how we can define independence with this joint distribution, and it's given by this independence for two. When we were talking about probabilities given events, was the probability, if the probability of intersection of A and B is the same as the probability of A times the probability of B. Here we have something similar. The probability of the joint that x equal to x and y is equal to y should be the product of the marginal probability of x times the marginal probability of y. This is indicating here. Okay. Of course, let's see one example to understand this better. This example is from web work. In this kind of problems, when we're dealing with the discrete case, typically you're going to start with a table like this. It says the joint probability mass function of x and y is given by, notice, P11 0.35, P21 0.05, P12 0.05, P13 0.1, and so on. So we can see that the first value corresponds to x, and the second value corresponds to y. The probability that x equal to 1 and the probability that y is equal to 1 at the same time is 0.35. So let's respond to questions. First, compute the conditional mass function of y given x equal to 3. A. Probability that y is equal to 1 given that x is equal to 3. In this case, we have to use the definition. The definition is this one. Is the joint distribution divided by P of x of x. So in this case, it's going to be the joint distribution at x equal to 3. Remember the first one, I mean, when you have the joint distribution, the first one is x, well, typically it's x, and the second one is y. So I have to put here first the 3, and then the y. But the y is 1. 3, 1, and divided by the marginal distribution of x. But I don't have it yet. Marginal distribution at 3. But no problem, we can get the marginal distribution. Marginal distribution of x. In this case, I have to sum px of 3. I have to look at the values in the table, and I have to add all the values of y, but such that the x is equal to 3. In other words, these ones. Notice I have the first value is x, remember? 3 in the x, 3 in the x, and 3 in the x. So I have to add this where x equal to 3, but the values for y, they are changing. I mean, y equal to 1, y equal to 2, and y equal to 3. So in this case, it's going to be probability of 3, 1, plus probability of 3, 2, plus probability of 3, 3. And this is equal to 0.05 plus 0.1 plus 0.05. And you will realize this is equal to 0.20. So the answer here above is probability of 3, 1. 3, 1 is 0.5 divided by 0.20. And if you compute this, you will realize it's equal to 0.25. So there you have the first answer for the part A is 0.25. This one. Next, are x and y independent? All right, to respond this first, we need to obtain the marginal probability for x and for y. Part B, we have x, pxx. Notice the values for x, they go from 1, 2, and up to 3. So I put here 1, 2, and 3. We already have computed the marginal probability when for 3, that is 0.20, so I can put it here. .20, I'm sorry, I don't know what happened. 0.20, but now I have to compute it for 2 and 1. How can I accomplish that? Well, add all the values in this and in these values for the function such that where the x equal to 2 only. 2, 2, 2. Remember that the x is the first value. So I have to add 0.05 plus 0.02 plus 0.05. That is 0.30. And do the same for the values where you have 1 and the x. 0.35, 0.05, and 0.1. You will get 0.50. Now do the same for the y. Notice that the values for y, in this case, they go from 1, 2, and 3. But I mean, they have the same range, the x and the y, but that is only a coincidence. I mean, they can have different values. But here we have 1, 2, and 3. If I want to get the values for 1, when y is equal to 1, I have to add all the values when y is equal to 1. This, and notice here I have y equal to 1, y equal to 1, y equal to 1. So I have to add all of this. 0.35 plus 0.05 plus 0.05. That is 0.45. Then the other one, when y is equal to 2, 2, 2, 2. 0.05, 0.2 plus 0.1, 0.35. And then 0.3, I mean, for when y is equal to 3, I mean, here the second value is 3, so I have to add all of these values. 0.1, 0.05, 0.05 is 0.2. Of course, you can verify that if you add these values, the sum is going to be 1. Because they are probability mass functions, right? That the ones we have learned before. All right. Now, what is the definition for independence? X and Y are independent if the probability mass the joint probability mass function is equal for the marginal probability of X times the marginal probability of Y. But this must be true for any values of X and Y. So that means if I can be able to find at least one value such that this equation doesn't satisfy, then I can prove that they are not independent. They are not independent. And this is the case. Notice. Take into account, for example, the value P11. Know that P1, 1 P1, 1 is 0.35. But this value is different if you get P of 1, P of X of 1 times Py of 1. Because this Px of 1 is what? 0.50 and Py of 1 is 0.45. 0.50 times 0.45 this is 0.225. So obviously this and this are not the same, right? So no, X and Y are not independent. Again, they are independent if this equation is true for any values of X and Y. If you find only one value for X and Y such that this is not true, I mean they don't have to be the same, of course. I use 1 and 1, but even if you find one value for X and one value for Y such that this equation is not true, then they can't be independent. So, no. X and Y are not independent. Part C. Compute the following probabilities. Probability that X plus Y is greater than 3. Part B. Part C. Probability that X plus Y is greater than 3. So in this case, I have to look at all the values such that the sum between x and y is greater than 3. The sum greater than 3. The only possibilities is when we have 3, 1, 3 plus 1 is 4, 2 plus 3 is 4, 1 plus 3 is 4, 3, 2 to 23. So no, notice, it's going to be all of these values. So consider all the values such that the sum of the x and the y is 4. It's more than 3, I mean. So it will be 3, 1, 2, 2, 3, 2, 2, 3, 2, 3, and 1, 3. So if you add these values, you will realize that this is 0.55. And it's the answer we have here. See? Now, x times y equal to 2. I think you can complete this 2. All the values such that x times y is equal to 2. All the possibilities such that x times y is 2. You can verify that the answer is 0.1. And the quotient x over y is greater than 2. All the values such that x and y, first x over y is greater than 2. And you can verify that the answer is 0.5. Very well. Now, let x and y be continuous random variables. We have defined the joint probability distribution for the discrete case, but of course we can also define this for the continuous case. In this case, we call that a joint probability density function. Is a function of two variables satisfying f of xy is greater or equal than 0. The integral from negative infinity up to infinity. Here we're going to be using double integrals. If you haven't taken a course of calculus 3, well, maybe for you this is going to be new, but don't worry. The integrals we're going to be computing here, I think they are not going to be very complicated. They're going to be only like examples that I'm covering here. So if this double integral, improper integral, dx dy is equal to 1. And the probability that x and y belongs to A is equal to the double integral over the region of the band A. And the marginal density functions f(x) of x is equal to the integral of the joint density function but over all the y values. And the same for the y. The integral is over all the x values. Yeah, I know. To compute the marginal for x, we need to, in the discrete case, we had to add over the y values. Here we have to integrate over the y values, and you want the marginal density for x, you need to integrate over the x values. And of course, independence. They are x and y independent if the joint density function is equal to the product of the marginal functions. So you can see that this is similar to the case of the case of the discrete case. I mean, similar to the discrete case, but here we have to be using integrals. Okay, so let's see one example to understand this better. Typically, when you are working with these problems of the joint density that is continuous for continuous random variables, you will start with a function of two variables. Or well, it could be even more variables, but here we're going to see only two. And again, if you haven't seen this before, don't worry. I think this is not complicated. I'm assuming that you know how to integrate basic integrals. It's going to be enough with that. Okay, here. So the stamp then paddy contest elections in two countries, Statland and Statupia. The proportion of support the paddy has in each country being modeled by the random variables x and y respectively. It is thought that the joint density function for the two variables is of the form, and notice we have the function for some constant k. Give answers to the following to two decimal places. First, find the value of a. All right, how do we find the value of a here? Well, notice we have one characteristic for this. If this is a joint density, then the integral over all the real numbers for x and y should be equal to 1. In this case, to respond to part A, we know that the integral from -infinity up to infinity of k times x plus 2y. I'm sorry, first let me write the definition as it is. F of xy, this should be equal to 1. But in this case, what is f of xy? Is k times x plus 2y. So we need to have the integral of k times x plus 2y, and should be, well, here depends the order, but let's skip with the order that we use here. dx dy. dx dy should be equal to 1. But notice, I know it says from -infinity up to infinity on x and from -infinity up to infinity on y. But in this case, notice how x and y, they are not defined for all the real numbers, only from 0 up to 1. So we have to put that here, 0 up to 1, 0 up to 1. Now, how to deal with this kind of integrals? A double integral, first, you need to compute this integral inside. You see, this is like a common integral of respect to x. How do we deal with the y variable? Well, in that case, you have to treat the y as a constant. So first, notice, this is a constant k, so it's multiplying, so I can take it outside this integral and outside this integral. So the answer is going to be equal to k times the integral from 0 up to 1 times the integral from 0 up to 1 of x plus 2y dx and then dy. And this is equal to k times the integral from 0 up to 1. What is the integral of respect to x? This is x squared divided by 2 plus, since this is a constant to y, the integral has to be 2x. Evaluate it from 0 up to 1 because the x goes from 0 up to 1. This one. This one. And we put here separately dy. Now, evaluate this integral, and don't forget the 2xy. Evaluate this integral. This is going to be equal to k times the integral from 0 up to 1 of what? Whatever you see the x, replace the x by 1, minus whatever you see the x, replace the x by 0. But notice we can skip this step because when we replace it by 0, 0 squared is 0, 2y times 0 is 0. So we can take only 1. It's going to be 1 squared divided by 2, 1/2, plus 2y times x, 2y times 1, 2y dy. You see? And this is equal to k times applied. Here I have two terms. So the first one is k times 1/2 y plus 2y squared divided by 2, evaluated from 0 up to 1. And again, I have wherever you see dy, replace dy by 1, and then minus replace dy by 0. But if when we replace by 0 dy, it's going to be on 0. So we're going to be left only with the, when we evaluate at 1, it's going to be k times 1/2 plus 2 divided by 2, they cancel out, y squared, that is only 1. And this is equal to k times 3 over 2. But remember, all of this has to be equal to 1. So set this equal to 1. Solve for k, and you will have k equal to 2 over 3. And that is the answer for the part A. Two over 3. Now, find the probability that the stat party had the support of more than half the population in each country. So in this case, part B, we look for the probability that x is greater than 1/2, comma, y is greater than 1/2. Why like this? Because it says find the probability that the standard patty has support more than half the population. X is supposed to be, X and Y, they're supposed to be representing the proportion of support the patty has in each country. I know that it's like a lack of information, but we're assuming that since it's a proportion, it's a number between 0 and 1. So x greater than 1/2, y greater than 1/2. Here, this integral is equal to 1/2 up to the highest value for x, that is the possible highest value is 1, and the same for y. So this goes from 1/2 up to 1, integral 1/2 up to 1 of, now your density with the value of k is 2 over 3 times x plus 2y dx dy. You have to compute this integral. When you do it, you will realize that the answer is 0.375. But try to do it as I did this one, right? Part C. And this is 0.375. Find the marginal density of the support in the stat lamp and evaluate it at x equal to 1/2. So part C, we look for the marginal density of x. That is the integral from negative infinity up to infinity of f of xy over y, over all the values of y. But we know that this is only the integral from 0 up to 1 of 2 over 3 x plus 2y dy. And this is equal from the integral from 0 up to 1. Notice, I can take out the constant 2 over 3 here. So it's going to be 2 over 3 integral from 0 to 1 of x plus 2y dy. And again, treat this as, we are integrating over y, so treat this as a constant. I mean the x. So this is going to be 2 over 3 xy plus 2y squared divided by 2, evaluated from 0 up to 1. And this is 2 over 3. Notice when we have to substitute by 0, it's going to be 0 and 0. Wherever you see the y, replace the y by 1 and 0. But when we do it for 0, it's going to be 0. So we will have left only the one for y, for 1. I'm sorry. So it will be x times 1 plus 2 over 2. They cancel out, 1 squared. And this is equal to 2 over 3 x plus 1. That okay? So let me see if I didn't do any mistake here. X plus 2y. So it seems to be correct. So this is the marginal density. 2 over 3 times x plus 1. Now it says here we have to evaluate it at 1/2. So at x equal to 1/2, the value of the density is 2 over 3 times 1/2 plus 1. And this is only 2 over 3 times 3 over 2. And this is only 1. So the answer for this is only 1. 1. Repeat the same for y, but now you will have to integrate over y. You are going to find the marginal y density. Yeah, I know, it's weird, right? Because to get the density for x, the marginal density for x, I have to integrate over y. That is true. If you want to get the marginal density for y, you will have to integrate over x. So do it, and you will realize that the answer for the part D is going to be 1 as well. So please verify that. And this exercise has one more question. Find the conditional density of the support in standard given that the party has 50% support in statopia. Evaluate the density at the point x equal to 1/2. So for this one, for the part D, we have to find, oh, I didn't define the conditional density, but no problem, I will do it right now. The density of x equal to x given that y is equal to y is defined as the joint density over the marginal density of y. So in this case, we need the joint density. The joint density is only the common function, right, with the constant 2/3. It's going to be 2/3 x plus 2y. 2/3 times x plus 2y. Divided by the marginal density of y. The marginal density of y, you have to get it in part D as I did it to get the marginal density of x. But anyway, you are supposed to have this 2/3 1/2 plus 2y. This is marginal density of y. I didn't compute it here. I didn't do the computations here. You are supposed to get it, okay? But you're supposed to get this answer. But we need it here because we need to divide this by this. And this is equal to what? 2/3 divided by 2/3, they cancel out. So we have only x plus 2y divided by 1/2 plus 2y. But we need to evaluate this at which value? Evaluate the density at the point x equal to 1/2. It doesn't say here, but if we say the standard has 1/2, we have to assume that the support from the statopy is the same, 1/2. So here, to get the answer, I have to evaluate both at 1/2. X equal to 1/2, y equal to 1/2. So we have the value of the density, f of x equal to 1/2, comma, given that y is equal to 1/2, is equal to substitute 1/2, 1/2, and 1/2. So we have 1/2 plus 2 times 1/2 divided by 1/2 plus 2 times 1/2. So you will realize that this is equal to 1/2 plus 1 divided by 1/2 plus 1, and this number is only 1. So the answer here is 1 for the part D. All right. One more concept here about expected value in this case. Let x and y be random variables. with joint density or mass function. Then the expected value of a function of the two variables h, x, y is given by the expected value of h, x, y that is equal to, if you have the discrete case, you have to sum over all the x and y values the function h of x, y times the PMF. And if you have the continuous case, it's going to be the integral from negative infinity up to infinity of h of x, y times f of x, y. And of course, this is the discrete case. And this is the continuous case. Now, related to this, we have something, a measurement that is called the covariance. Covariance is defined as the expected value of x minus its mean times y minus its mean. And this is going to be equal to the product, the expected value of the product minus the expected value of x times the expected value of y. This is called the covariance. Note that if x and y are independent, then the expected value of x and y is equal to the expected value of x times the expected value of y. So that the covariance of x and y becomes 0. What is the covariance for? Covariance, this is more for statistics, but covariance can be interpreted as the degree of joint variability between the values of the variables, the random variables, x and y. Very well. Yeah, covariance, I don't know if you are familiar with the concept of variance. So variance is a measure of variability, but that applies only to one when you have only one variable. You want to know among all the values for the given variable, what is a measurement of variability or spread for those values. you can use something called variance. Well, in this case, we have two variables. We're trying to measure what is the spread variability between the two values for x and y. That is the value for covariance. If the two values are independent, the covariance is zero, no variability, because they don't have any kind of relationship. All right, let's see one example. Example. All right, Canadians who visit the United States often buy liquor and cigarettes, which are much cheaper in the United States. Maybe they are much cheaper in Mexico. However, there are limitations. Canadians visiting in the United States for more than 2 days are allowed to bring into Canada one bottle of liquor and one carton of cigarettes. A Canada customs agent has produced the following joint probability distribution of the number of bottles of liquor and the number of cartons of cigarette imported by Canadians who have visited the United States for 2 or more days. And we have bottles and cartons of cigarettes. Find the marginal probability distribution of the number of bottles imported. First, number of bottles. Here, part A, probability of 0 bottles is equal to what? Again, you have to add over all the values when the value for the variable battle is 0. So that means these two, right? Here, battle is 0, add all of this column. Then it's going to be 0.67. And probability of 1 battle, do the same, but for all the values when the battle is 1, is 0.34. 33, I'm sorry. Now, B. Find the marginal probability distribution of the number of cigarette cartons imported. Well, in this case, we need to have two tables. First, for bottles, the positive values are 0 and 1. We already have the. Oh, I'm sorry. I got confused. I thought we have to find two of them, but no, it's asking for the other case. Marginal probability distribution of the number of cigarette cartons. So 0 and 1. So probability of 0 carton. I'm sorry if I'm not pronouncing well this word, carton. 0 is equal to, again, add for all the values where cartons of cigarettes is 0. Here, 0 at 0.6 plus 0.16 is 0.76. And probability of 1 carton is add for all the values where this variable is equal to 1. 0.07 plus 0.17 is 0.24. Very well. Now, compute the means and variance for the numbers of bottles. Mean and variance. This is something that we have done before, like the discrete case for one single variable. So in summary, we can say that this is the part C. Part C, bottles probability 0 and 1. For 0, we have 0.67, 0.33. 0.67, 0.33. The mean, remember, expected value of bottles is equal to each number times its probability, and then add 0 times 0.67 plus 1 times 0.33. And you will realize this is only 0.33. Now do the same for the cartons of cigarettes. We have 0 and 1 and the probability. The values are 0.76, 0.24, and again the expected value for cartons is equal to 0 times 0.76 plus 1 times 0.24, and this is of course only 0.24. And there you have expected value, the mean for, well, was asking for the means for bottles, and the part is for mean of cigarette. Well, I'm sorry, no problem. But now the variance for bottles. Variance for bottles. The variance, it was each value of the variable, 0, for example, minus the mean, times the corresponding probability for the value, in this case 0.67. 0.67 raised to the square, plus the other value, 1 minus the mean, 0.33, times the corresponding probability, 0.33. And if you do this, you will realize that this is equal to 0.2221. 0.2211. Let me verify the answer. Yeah, it is correct. So this is the answer for the variance. You can do the same for the cartons of cigarettes. Variance is going to be equal to 0 minus 0.76 raised to the square times the probability 0.76 plus 1 minus 0.24 raised to the square times 0.24. I'm sorry, I did a mistake here. Should be 0 minus the mean, and the mean in this, or the expected value in this case, is 0.24. So 0 minus 0.24. And this is equal to, if you compute this, you will realize that the answer is 0.1824. So now I have the mean variance for the two cases. And next, part C, part D. Part C, part D. Finally, part E. compute the covariance and the coefficient of correlation. The covariance, by definition, we have it here, is the expected value of x times y minus the expected value of x times the expected value of y. So first, for the part E, first we will compute expected value of x times y. Now from the definition that we have, this is only the multiplication of all the cases between x and y. I mean 0 for the x of bottles, 0 for the cartoons, times the probability .6. Yeah, I mean, how am I computing this? I have to consider all the cases. 0 for cartons, 0 for bottles. The joint probability is 0.6. Plus 0 for cigarettes, 1 for bottles. And the corresponding probability is 0.16. The joint probability. 0.16 plus now 1, 0. 1 times 0 times the corresponding probability, that is 0.07. Plus, finally, 1, 1. 1, 1, the corresponding probability is 0.17. And notice, this is going to be 0, 0, 0. It's going to be only 0.17. Now, once we have this, now covariance of xy, you can use this formula. Covariance is equal to expected value of x times y minus the product of the corresponding means or expected values. So it's going to be 0.17 minus the mean of x, or bottles in this case, that is 0.33, times the mean of y, that is, or cartons of cigarettes, that is 0.24. If you do this, you will get 0.0908. Finally, the coefficient of correlation is denoted by this symbol rho, like a rho, root letter rho, and is equal to the covariance of x and y divided by the square root of the mean of x times the mean of y. So we need the covariance. In this case, it's going to be, so we need the covariance. The covariance is 0.0908 divided by the square root of the mean of x. The mean of x, well, in this case, x is bottles, 0.33, and the mean of y, that is cartons, 0.33 times 0.24. No, I'm sorry. I did a mistake. It's not the mean of x. No, I'm sorry. It's the variance. I'm sorry. I'm really sorry. It's the variance. Variance of x times variance of y. I'm really sorry. Anyway, we already have the variance, right? Variance for bottles is 0.2211. 0.2211 times variance for y, 0.1824. Yeah, I'm sorry. It's variance. Square root of the product of the variances. And if you compute this, you will realize that this is 0.452146. And there you have. See you in the next video.